Hello everybody, my name is Filip LJUBINKOVIĆ. I'm working as a researcher at the University of Coimbra. Today I will speak in English, although later we can also discuss in Serbian and in English. So this is the title of my presentation today. It's called Steel Box Girder Bridges with a Curved Bottom Flange Design Rules. So first I will say something general about these kind of bridges with a curved bottom flange, and then I'll say something more about the experimental and numerical studies we carried out, and then finally about the design proposals. So in this table you can see as many as 20-25 bridges that were built successfully in the previous maybe 20-30 years. And what is so special about these bridges is that the bottom flange of these boxes is actually a curved panel. It's not a flat one. This is mainly done because of some aesthetical reasons, but also there are some structural benefits. Now, if we take a look only at the bottom flange, the curved bottom flange, we can see that it can be described by many geometrical parameters. However, we commonly use these two non-dimensional parameters, aspect ratio and the curvature parameter zeta. So aspect ratio is the ratio between the length and the width of the panel, and zeta parameter is the parameter that takes into consideration pretty much all the other geometrical parameters here. And in case of the bridges, it can go up to 300, sometimes even beyond 300. Now, if we take a look in this example of the bridge with a curved bottom flange that was built in Croatia, we can see that for this geometry, the zeta parameter is somewhere around 88, which is way beyond 1. And this is now the problem because we know that the Eurocode 3 part 1.5 is valid only for the zeta parameters up to 1, so pretty much for the flat panels only. And this is now the main motivation for this work, because we don't know then how to design these kind of bridges for the zeta parameters beyond 1. And this topic was studied in two research projects. One is the Portuguese national project, Ultimate Panel. The other one is the European RFCS project, Outburst. In the first project, we focused mainly only on the curved panel under different loadings, such as compression and shear, and developed the rules for this kind of fundamental loadings. And then in the second project, Outburst, we integrated actually the bottom flange inside of this box girder, and then studied the behavior of this kind of cross sections with a curved bottom flange. And this is the topic of today's presentation. More specifically, the objective of this presentation is to show how we verify the applicability of the use of this MV interaction criterion that already exists in a Eurocode, in a new version of the Eurocode. So this criterion is used already for the trapezoidal box girders. We wanted to check if it's safe to use also this criterion in the case of the curved flanges, box girders with the curved flanges. And the main challenge in order to apply this rule was to define first the bending resistance and the shear resistance of this kind of cross-section, because these two values were unknown completely at the beginning of this project for this kind of cross-sections. So in order to study the MV interaction criterion, we carried out first the experimental study, focusing mainly on this region close to the intermediate support, because this is exactly the zone where the MV interaction occurs. And we prepared specimens that we tested in our laboratory here at the University of Coimbra. We applied such loading to imitate this kind of behavior and to get the MV interaction here close to the intermediate support. Now, using these experimental results, we built up a numerical model. Here you can see the numerical model, and here you can see also the behavior of this numerical model. We compared the failure modes with the experimental ones, and also the load displacement curves. And as you can see, a very good match of the results was obtained between the numerical results and the experimental results. Now that we validated our numerical model, we wanted to extend the scope of the geometrical parameters. So we extended the zeta from 0 up to 300. We studied also aspect ratios up to 1.5, and we varied different configurations of the stiffeners, flat stiffeners, trapezoidal stiffeners, so all sorts of configurations, and we came up with a number of 210, if I'm not mistaken, number of different geometries. The main objective, of course, for the study of the MV interaction was to build this MV interaction diagram, which consists of these 10 numerical points. So for each geometry of these 200, we wanted to see the entire spectrum of behavior from the bending all the way to shear dominant failure mode. And all these intermediate points, the gray ones, correspond to the interaction between the two. So 10 points for each geometry led to 2000 numerical models. Now, using the numerical results, we proposed analytical solutions separately for the bending and for the shear. First, I will say something about the bending resistance model. So as you can see, this formula is completely the same like the one from the Eurocode for the trapezoidal stiffeners, trapezoidal box girders. However, what is new here is actually the definition of these effective properties of the cross section. And for that, we proposed a curved panel approach. It's a 5-step approach. I will go just quickly through those 5 steps. First, we assume conservatively that the bottom flange, although it's curved, is subject to uniform compression, and that with that assumption, we apply the rules that were developed in those 2 projects that I mentioned to obtain the effective properties of the curved bottom flange under uniform compression. Then, using the effective properties of the bottom flange, we recalculate in the 3rd step the position of the neutral axis. And then in the 4th step, for this new position of the neutral axis, we calculate the effective properties of the flat webs. And then finally, in the 5th step, we have the effective properties of the entire cross section, so we can substitute this value in this formula for the bending, and this is how the bending resistance is obtained. So this is summarized. All 5 steps of this project of this model are actually summarized in this flow chart. Okay, that was the bending resistance model. Now I'll say something about the shear resistance model. We know that using the Eurocode formula, we can calculate the shear resistance of the flat part of this cross section. However, we were particularly curious about this curved bottom flange. We wanted to see to what extent this bottom flange also participates in the shear resistance. So we ran many analyses, and by integrating the shear stresses here in the bottom flange, we came up with this very convenient formula for the calculation of the participation actually of this bottom flange in the shear resistance in a function of zeta. And then using this formula, we proposed a so-called extended web plate model. Why is it called like that? Because we extend this flat part of the web, so this green zone, onto this horizontal imaginary line, so that we convert actually this realistic geometry into this fictive trapezoidal cross section, and then we apply the rules of the Eurocode onto this extended web. That's why the name extended web plate model. And then we also include somehow in this formulation this LW formula that we obtained for the shear participation of the bottom flange. Now, finally, that we know now how to calculate the bending resistance and the shear resistance, we can now complete our work and verify the validity of the MV interaction criterion. This is done in these 2 graphs. So we compare the analytical results with our numerical results, these points. And as you can see, for the entire scope of this study, in all points we satisfy the safety. So we can safely apply this MV interaction criterion. And then we calculated the partial factor gamma m separately for the bending and for the shear resistance model that we proposed. And we came to the conclusion that the same partial factors that are used for the trapezoidal box girders can be also used in this innovative bridge cross section. Finally, for more information, you can search in all of these published papers and ECCS document that is on the way now. So where we described each and every part of this study that I showed today. Some parts of this work were already included in the new version of the Eurocode for the steel bridges in Annex B. So you can also take a look there when it's published, I think next year. So thank you for your attention. If you have any question, you can ask me or you can send me an email. Thank you very much.